All right, recording is rolling. It is Tuesday, February 6th. So I have some puzzles for you guys. We're going to do these 6 questions right here. Let's go ahead and circle them. Number 32, number 55, 56, 64, 65, and the very last one says test number 9. Do that. All right, so just those 6 questions fit pretty well in my last class period. Right. Before I get rolling too far, check focus, guys. Double check focus. Make sure you're not missing any assignments. I still haven't handed back yet the harmonic motion quiz from like 2 weeks ago because I have about 10 students who still haven't turned that in. So here, last couple of days to opportunity to get that in because everyone wants the quiz back. It's supposed to be turning on time, so I want to get that back to you guys. Okay. All right, so you guys remember yesterday we started a new topic. We're looking at thermodynamics. I gave you guys these thumbnail notes right here. We did a whole PowerPoint, looked through laws of thermal energy transfer, sort of thing, right? Temperature scales. Right? So let's apply that to these puzzles. So these are out of your textbook. But I typed them up so that we all have different numbers. My numbers are different than your numbers, but otherwise we have all the same premise. Right. So number 32, I got water flowing over a waterfall that's so many meters high. If the potential energy, right? Oh, I remember that last semester. Right? Potential energy of water is converted to thermal energy. Okay, this is new. Well, from yesterday. Calculate the temperature difference between the water at the top and bottom of the fall, right? Gave you guys gravity field of Earth and also the specific heat capacity of water, right? So here's kind of the thought process we're going to lead into. It's kind of related to a question from last semester. Guys, everybody look up here? Everybody writing this down, right? So you guys remember last semester, there's a question, Galileo drops the ball from the top of the Leaning Tower, and how fast is it going at the bottom of the tower? And one way you could solve that was with this conservation of energy method, which we're about to apply, but for thermal. Right? So, guys, what kind of energy at the very top of the tower? Potential energy, right? And that took the form mgh, right? Mass times gravity field times height. Right? And then what type of energy right before it hits the ground? Energy of motion, we call that kinetic, and that took the form 1/2 mv squared. Okay? Now, since energy was conserved, we say sum of energy initial equals sum of energy final. You can equate those terms, and then you can solve for stuff. And then, like what was the crash speed? And you can get that expression. Right. Now, the question we're answering now has to do with the waterfall. Right. Ooh, that looks kind of like this. Right. Except, well, it is a continuous stream of like mass flowing of water. Right. Maybe if we like focus on a water droplet or something, or maybe we could say this is like a continual process. Right. And I bet it starts off with all potential energy at the top of the waterfall. But when it gets to the bottom and it hits the pool at the bottom, like a splash, do you guys think if you had a thermometer on that water, its temperature would go up a little bit? Right? Because instead of saying it goes to kinetic, we're going to say it goes to thermal energy. And we're going to have a new expression for that. Well, new as of yesterday. Okay. Yeah, and then we can solve for what is that temperature rise. So number 32. Right. Get you guys a picture going here. Here's like a waterfall. And you can splash, right? There's a little thermometer down here. So like a little thermometer. Right? So what's the temperature rise? It's a splash in this pool. Right? Right? We got some height change in this water. There you go. H, so some gravity field, G, like that. Right? And the premise, like the framework we're going to use to solve this is this right here. Sum of energy at the top of the waterfall equals sum of energy at the bottom of the waterfall. Right? Kind of starts out the way the Galileo problem started out, right? Okay, it's true for the initial condition too, right? What expression do you think I'm going to write right here? MGH, exactly. Yeah, MGH, right? And maybe it gets a little weird because what exactly M are we talking about? Maybe you could focus on a single water droplet is fine, right? Or if you want to do like an aggregate approach, I guess like, again, it's a continuous stream of water, right? Let's see what this looks like on the other side. Maybe this make more sense mathematically when we get the whole thing down, right? Now, where does the energy go? Well, it's going to go into the thermal. It's going to raise the temperature on this thermometer, right? Now that you guys saw from a PowerPoint yesterday. So let me do a little side note here and then go back and fill it in, right? There was a equation you guys saw yesterday, one like this. Delta Q equals MC delta T. Okay, so let me remind you guys what each of those parts means. Okay. Delta Q, okay, that's a change in something, right? And Q is, in this case, thermal energy. So this is a transfer of thermal energy. I could say, go ahead and spell that out. Transfer of thermal energy, right? Which goes by another name that's called heat, right? So whenever I say heat, I'm talking about transfer of thermal energy, right? M, we're talking about the mass of the water in question, right? C is, okay, it's called specific heat capacity, right? So tell you guys something right now that I told you yesterday, just a review. If you put a pot of water on the stove, right, you got the liquid water, but you got the metal pot also, and it's all on the same stove range, right? Does that metal heat up real fast? Yeah. Now water, it eventually heats up, but it takes a long time. It might take a few minutes to boil. Right? So it's different materials it's easier or more difficult to heat them up. And water, turns out, has a really high specific heat capacity. We were looking at some tables yesterday, and it's like the largest value compared to all the other materials we were comparing to. Right? It's really hard to change the temperature of water. Okay? So water's not going to probably heat up very much for some particular given energy input. Right? And that's what this delta T is, right? This change in temperature. Okay, right, guys have it? Right, right. Well, if delta Q is some form of energy, which you can measure in joules. This could be in joules, right? That's gonna fit nicely into this equation we have set up here, because these are energy terms measured in joules. So this is gonna go MC delta T, right? Right. So okay. So by falling some height and then splash, you're gonna raise the temperature some amount for some material. Right, guys, follow that? Right. No, I think I gave you all these numbers, except I didn't really give you the mass of water in question, right? Are we talking about a droplet or talking about continuous flow, right? Doesn't matter because it cancels out right there. Right. Okay, so now it doesn't even matter that I didn't tell you how much mass we talked about. Okay. And here's our goal. What is the change in temperature of the water? Okay. At some point I got to plug in numbers, so I'm gonna go ahead and do that right now. I said go ahead and use 10 meters per second squared for a gravity field. Right there. Now my waterfall is this many meters tall, but I think that's different for you guys. We all have different height waterfalls, so careful about that. Right. Now, specific heat capacity of water. I did give it to you in the question. I said it's 4,182 joules per gram, joules per kilogram Kelvin. Right there. Right. I've seen slightly different versions of that number. I've seen anywhere between 4,180 and 4,186. So for the sake of time, I just copied that down. There we go. And then, okay, here's what we're solving for. What is the change in temperature of the water? Okay. How much is the temperature going to rise due to splash from that waterfall? You guys see the one algebra step to finish this off? I'm just going to divide down the specific heat capacity of water. So change in temperature of the water is 2 meters per second squared times 95 meters tall waterfall, all divided by 4182 joules per kilogram Kelvin. Put it all together in my calculator. That times that divided by that. I'm getting, it's like a fraction of a degree. It's this many degrees Celsius. I could say degrees Celsius or Kelvin. Both those would be okay because we're talking about a change, right? The change in temperature. Right? Scale it by 9/5, which is approximately 2. You'll get the change in Fahrenheit, right? So, yeah, it's not even 1 degree Fahrenheit for that matter, right? Make sure that's an answer choice on my paper. Do I see something that looks about like that? Yeah, see it right here. Bam. Good to go. Are you guys also getting an answer choice on your paper? All right, so working out for everybody. All right, so you guys get the premise. It's all working out. Are we good? All right. All right, next one. Number 55. So many grams piece of mystery metal. Okay, I got a really hot temperature. Maybe we had this mystery metal on the stove, right? is placed in so many grams of water at pretty much room temperature, right? Okay, again, everybody has a little bit different number. Mine says 20 degrees Celsius, right? But let's do a pause right here. Let's do a little side quest, right? It's 20 degrees Celsius. What is that in Fahrenheit? How would you find out? You guys see a poster in there in the room by that door over there, or if you look on your thumbnail notes, it tells you exactly how to convert Celsius to Fahrenheit. Or sorry, this one right here, Celsius to Kelvin. Here's Celsius to Fahrenheit. Okay, so take the temperature in Celsius, multiply by 9/5, and then add WT. Okay. So if I have 20 degrees Celsius water, what is that in Fahrenheit? So I'm going to do 9/5 times my 20 degrees Celsius water plus 32. Okay. It's saying 68 degrees Fahrenheit, which is about the temperature of this room, right? So there you go. 20 degrees Celsius is kind of like a air conditioned room. You can think of it like that. Room temperature on the cold side. Okay. Okay. So you guys, okay so far? So back to here. All right. Anyway, we're gonna put this really hot piece of metal inside this room temperature water, and they're gonna reach an equilibrium temperature. Do you think it's gonna heat up the water a little bit, and the metal's gonna cool down a lot until they both reach the equilibrium temperature value, which is right there, right? What is the specific heat of the mystery metal? Ooh, hey, and because every material will have some different set of material properties, including specific heat capacity. When we solve this question and get an answer, I bet you could look up a table of values and say, oh, well, that must be copper or that must be zinc, right? Because it would match that material property, right? How difficult is it to heat up or cool down this particular piece of metal, right? You guys go with that premise too? Okay. All right, so solve this out. I do want to get you guys a picture for this one. It's number 55. 55. Okay. So it's kind of go like this. Maybe I got this glass of water, like a beaker of water, something like that. All right, it's all water. Okay. At room temperature, just sitting there, and then I get drop in this this really hot piece of metal, right? And it's going to start emanating heat into the water, right? Okay, so that's a transfer of thermal energy, isn't it? Right, transfer of thermal energy, right? I'll call it like a delta Q, right? There's a transfer of thermal energy from the metal into the water. Right? Oh, you know what? I think this was probably like a conservation of energy type thought process. Do you guys think that the loss in thermal energy from the metal is exactly picked up by the water? You guys think? Right. I'm gonna do one more thing. I'm gonna tag a negative sign onto one of those terms, right? For like import export, right? So the metal is exporting some number of joules of thermal energy. The water is importing exactly that same number of joules of thermal energy, right? There's an energy transfer, right? You guys got that premise? Okay. Okay. All right. Now the last question with the waterfall, we were saying, okay, well, the heat transfer is going to have something to do with temperature change. How much temperature change? Well, it has to do with the mass and the specific heat capacity. This is this expression right here, MC delta T. Okay, so you guys see where this is going, right? The next step. I'm going to take this MC delta T and substitute it in for each one of these, except one's for the metal and one's for the water. Okay? Okay. Great. Good. All right, I'll check it out. So I'm going to say, keep my negative sign for exporting energy. Right? The mass of the mystery metal times the specific heat of the mystery metal, which, by the way, that's our goal. Trying to solve for what is that number? Times the change in temperature of the metal. So, right. Yeah, well, getting there. Oh wait, no. Is equal to mass of the water, specific heat of water, times change in temperature of the water. Okay. Okay, so the energy was exactly transferred. Whatever was exported by the metal was picked up by the water. So that's MC delta T of the metal, therefore is MC delta T of the water. Throwing that negative sign. Okay. Okay. I'm going to do one more substitution before I put in numbers, which is this delta T, the change in temperature. I'm going to rewrite that as final minus initial. Okay. So I'm going to do mass metal, specific heat metal, right? Temperature final minus temperature initial metal equals mass water, specific heat water, temperature final minus temperature initial water. Okay. All right, good. Right. They both have the same final temperature because eventually they reach that equilibrium value, which is the same for both, which is the number I gave you. You have everything. You should have everything except for the specific heat capacity of this mystery metal. Okay. Okay. So let's start plugging numbers in. See what I got. So I have 30 grams right here. Right. Interesting. I'm going with grams on this one. You guys know in this class they usually stick to kilograms. That's the base SI unit. So careful with that. In this case, the number's gonna be okay. Specific heat, the metal, we're gonna solve for. Right. Looks like my mixture went to see this many degrees Celsius from right. Initially, the metal was this crazy hot. Right. Ooh, Celsius. Is a change in temperature in terms of Celsius the exact same as the change in the temperature in terms of Kelvin? Yeah, because change in 1 Kelvin, change in 1 degree Celsius is the same change, same value. Those two different scales are systems are like scaled the same, right? Two different systems scaled the same, temperature and Celsius and Fahrenheit. Right, water. I have this many grams of water. Right. Now, what's the specific heat capacity of water? Okay, now, okay, here's a little tricky right here. Specific heat capacity of water, right? And you might be thinking, okay, I don't see the number printed in the question, but I remember we just used it for the waterfall. Be careful about that, because for the waterfall, I put it in joules per kilogram Kelvin, right? That's actual base SI units, right? We're not going to use that number. We're going to use instead, you guys see way down here in the bottom left of the page, I give you specific heat capacity for water in different states. And the liquid version is right in the middle. It says 4.18 joules per gram Kelvin. You guys see that? 4.18, right? It's off by a factor of 1,000 compared to what we did for the waterfall. Waterfall was in joules per kilogram Kelvin, but here we're working with the grams, little tiny grams. So it's only 4.18. Okay? Right. That's what we're going to do. It goes right here. 4.18 joules per gram Kelvin. It's right there. Okay. All right. You guys get that? Okay. And then temperature final, this many degrees Celsius from temperature initial, this many degrees Celsius. Great. Boom, 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 boom. Right. It's all there. So all I gotta do is just divide, and got the answer. Right. So specific heat capacity of the metal is equal to, right, all the stuff on the right divided by, see this on the left, negative and negative cancel out, so have a positive value, which is good. That times that times that divided by that, and then that. Right. I'm getting this many, it'd be a joules per gram Kelvin is what that is. Joules per gram Kelvin. Okay, because specific heat capacity is measured in, it'd be either joules per gram Kelvin or joules per kilogram Kelvin. Okay, one or the other. Okay, let's make sure that number is a answer choice. Yeah, it's right here. Bam, there. Okay, you guys getting a answer choice on this paper too? Working out. All right. That. All right, I'm gonna move on to the next one, number 56. Number 56. If anybody needs, that's right there. So many grams sample of water at so many degrees Celsius is mixed with a different mass of water at a different temperature, right? What's the final temperature of the mixture? Okay, so I got some mass of hot water and some mass of cold water, and I'm going to mix them together. Ooh, I bet the equilibrium temperature is going to be somewhere between those two values. What's the equilibrium temperature going to be? Okay. We're going to use the exact same thought process that we did for the previous question that we just finished. Okay. Except what we're solving for is going to be a little bit different. So 56. Right. It can still say the energy transfer is going to be the same for both. Like here, delta Q of mass A equals delta Q of mass B, right? And then I'll throw in a negative sign for one of them, right? Whatever heat energy is exported by one of the masses is exactly imported by the other. That's all that means, right? Thermal energy transfer, right? And then here, do this. Go mass A, or throw in a negative sign somewhere, right? Mass A times specific heat capacity of water times the change in temperature of the water for that specific mass, right, is equal to, and then I got MC delta T on the other side, maybe for mass B, specific heat capacity of water, and change temperature of the water for mass B, right? But do another substitution. Instead of changing temperature, I'll call it final minus initial. So let's do that. Okay, negative mass A, specific heat capacity of water, final temperature minus initial temperature for A equals, say, mass B, specific heat capacity of water, final minus initial for B. Okay. All right, that all right? That's set up. Okay. All right, so while you guys are catching up to there, right, let's go over why the setup is working, right? So I'm mixing two different masses of water, right? So I got maybe got this glass of water, this glass of water. I'm gonna right, mix them all in this like big container. They're all mixing together. Okay. Some of this water is really hot, and some of this water is cold, and they're different masses. So I bet the larger mass is gonna like weigh more towards that final temperature, right? Okay. So what is that final temperature gonna be? Right? Well, the hot water is gonna export its energy, and the cold water is gonna import exactly that same amount of energy. That's that premise right there. That's the first line. Right. Now, how does that translate to temperature? Well, I'm going to substitute in for delta Q and C delta T, right? And do that for both parts, right? Okay. Okay. And then for delta T, all I did was say, well, that's final minus initial. Okay. Now notice that final temperature is what we're solving for, and that shows up in two different places in the equation. Okay. Right. Okay, so is everybody up to that point? Okay. Okay. All right. Let's start plugging in values. So I got 600 grams of 80 degrees Celsius water. So got 600 grams. Okay, I went with grams again. Up to, right. Although, you know what? Specific heat capacity of water. The fact that it's water and water. Can I just go ahead and cancel out specific heat capacity on both sides? I should do that. I mean, you can plug in a number, but it wouldn't matter anyway. It goes away, right? Okay. If it was olive oil and olive oil, I bet it'd be like the same answer at the end, right? As long as it's the same material, you can cancel both sides. Okay? So I got 600 grams right there. So then multiply by, okay, I don't know what the final temperature is, that's the question, but I know that my 600 grams started at, what did it start at? 80 degrees Celsius. Okay, so it was pretty hot water right there, 80 degrees Celsius. That's equal to, and the other mass is 300 grams. Final minus, okay. The initial temperature was about room temperature, 3 Celsius. Okay. There. Boom, boom. Okay. All right, you guys good there? Okay. All right, now there's probably a little bit different ways you could finish this out, whatever algebra process you like. I'm gonna do distribution. Right. If you have a different way you want to finish it out, then that's okay too, as long as you get one of those answer choices. Right. I'm gonna distribute. So also I'm gonna drop my units just for a step here, just to make this a little easier. So I'm getting like 600 TF plus 648, 0, 0, 0 equals 300 TF minus Let's do 6,0,0,0, something like that. Okay. All right. So see this part of the algebra process, I have 4 terms. 2 of them well, have common units there, and 2 of them have the target variable that I'm solving for. So I'm gonna get like terms together. All right, bringing that over here. Right, then add that over here. Right, and finally divide both sides by this coefficient. Let's get that. Yeah. Right. And then okay, well if I kept units along the way, here, I just go ahead and restore the units right here. It's degrees Celsius, right? You're gonna get some temperature in degrees Celsius at the end of that process. All right. Yeah, and I see that as an answer choice right there. So circle that. Boom. It's one more down. All right, that's working out for you guys too. Working out. Well, all right. So here's the page right here. If anybody extra, look at that. Let's go on to the next one. I'm going to skip right over here to number 64. 64. Right. We're just going to do the one today circle then. I'm not going to worry about the other ones. Right. So we're just doing 6 questions today. I think today. Number 64. How much heat? Okay, so that's like transfer of thermal energy, right? So how much heat? Maybe you could quantify in joules. Right? Looks like all the answers are in kilojoules. Are needed to turn so many grams of ice at negative 10 degrees Celsius into steam at like above 100 degrees Celsius. Right? Right. Now this one's going to be a little lengthy. It's going to be like a 5-part process. Right? You guys see this diagram in the bottom left corner of this paper? Okay. Now this was a graph you guys saw yesterday on the PowerPoint, and you also have on your thumbnail notes. It's your top right poster on your thumbnail notes. Right? You guys see temperature versus heat energy. Right? And there's a curve that kind of tends up to the right. Right? Put some water on the stove. Right? As you add heat energy, that's going to the right on the graph. It's going to generally raise the temperature. Right? Except when it's changing phase. We went through this yesterday too on the PowerPoint. You guys remember when it's melting or when it's boiling, the temperature gets stuck for a while, right? So you're adding energy, but the temperature is not changing, it's just changing phase, right? So we're gonna have to do like this 5-part process. We start with those like sub-zero cube of ice. The first leg of the process is we need to bring it up to the point where it starts to melt. The second leg of the process is we need to melt the entire ice cube. The third leg of the process is now we need to take the water all the way up to the point where it starts to boil. The fourth part of the process is we need to boil all the water away. And the fifth and final part of the process is we need to continue heating that steam up to the target temperature. Boom, 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 boom. Right? You guys got that? All right. So let's do that 5-part process right here. Right? I figured out last class there's a certain way I can put this all on one paper. 64. Okay, so you guys got that graph in mind, right? So I'm gonna label this part 1, part 2, part 3, part 4, part 5. Right? At least I think this will look good for the video, and hopefully you guys are taking notes. Right? And so there's some transfer of energy. That's the question. How much heat total? Right? So I'm gonna do delta Q. Right? For each of these 5 steps, and I'm going to add it up together at the end. Right? So the last step is going to be the sum of these 5 parts. Right? So delta Q equals. Right? Now the first part is I need to warm up the ice cube until it begins to melt. So that's MC delta T. right? And the C is specifically for solid ice, right? And then delta T to bring it up to where it starts to melt. Okay? Then the next part, so part 2 of the process is I need to melt the ice, right? So, okay, so this is like ice, this is like melt, right? Now this is the part where there's no temperature change. So I can't use MC delta T. I have to use that other formula you guys saw in the PowerPoint yesterday, which is M delta H. So this is the same mass, ice order, right? Times the heat of fusion, right? To melt the ice cube, right? Right. Once I completely melt the ice cube away, now I got 0-degree liquid water. I need to warm up that water to where it begins to boil. So we're back to delta Q for the water equals MC delta T. But this is for water, liquid water. Okay. Right. Then when I hit 100 degrees Celsius, the water starts to boil. I need to boil all the water away. And this is, I think, going to take the most energy out of this whole process. This is the step right here, boiling all the water. So delta Q boil. So now we're back to M delta H, but this is heat of vaporization. So this was like fusion. This one's vaporization. Right? To vaporize a lot of water. Right? And then finally, last part of the process, delta Q for the steam, right? Because I need to continue heating the steam. So I'll keep adding energy to it. So we're back to MC delta T. This is for steam. Okay. Boom. Right. Are you guys okay with the 5 parts? Sure. Right. So every one of this says delta Q equals. That's like heat, thermal energy that I'm transferring into it. I'm going to the right on this graph, so I'm out to the right, to the right, to the right, to the right, to the right. Okay. And then 3 out of those 5 parts, the temperature is rising, and then 2 of the parts where it's flatlining, well, that's where it's changing phase. Okay. And so let's get some numbers in here. So say equals, I'm just gonna keep going right here. Right, however you guys want to organize your notes, I'm just gonna keep putting numbers out to the right. Maybe I'll change ink color. Maybe I'll make it stand out a little bit better. Okay. So I have 15 grams. Okay, interesting. I went with grams. Yes. Okay, so I guess we got grams, 15 grams right here. 15 grams. Right. Well, if I'm working with grams, then the specific heat capacity better also be the number in terms of grams. Okay. And all 5 like specific heat values and heat of fusion and vaporization, they're all down here, right, the bottom left. And they're all in terms of grams. So I got joules per gram Kelvin, joules per gram. You guys see that all the way down? Right. Okay, so I can just use those numbers straight up as they are because they're applied to masses and grams. Okay. So I'm going to go for ice 2.09 joules per gram Kelvin. Got my joules going on. Okay. And then change in temperature. Well, guys, if we started with negative 10-degree ice and we have to bring it up to 0 degrees to start to melt, what is the change in temperature? What's 0 minus negative 10? Positive 10. Right? I could say either degrees Celsius or Kelvin, right? Because it's a change, right? Boom. There, that's the first one ready to go, right? I'm going to set up all the other ones, and then I'll get numbers for all these, and then add them all up, right? So now I need to melt that ice cube. So I'm looking at 334 joules per gram to melt the ice cube. So that's so 15 grams at 334 joules per gram. Okay. Next part, I need to boil away the water. So MC delta T. So the mass is still 15 grams. Specific heat capacity of water, I'm going to use the 4.18 joules per gram Kelvin. And then change in temperature, because we're going from 0-degree water to 100-degree water. That's a change in temperature of what? 100 degrees Celsius, right? It's 100 minus 0, right? 100 minus 0 is 100. You can also call that 100 Kelvin. That's okay too, because climate change. Okay. Right. Then, fourth step, I need to boil this all away. And I see it says heat of vaporization of water is 2,260 joules per gram. Woo! It's a big number there. So I'm taking 15 grams and 2,000 and something, 2260 joules per gram it takes to boil all the water away. into steam. Okay? And then there's one more part of the journey. Got 2.01 joules per gram Kelvin to continue heating the steam. So MC delta T, mass is still 15 grams. C is now 2.01, that's joules per gram Kelvin. And delta T, well, okay, my final target temperature is 150 degrees Celsius. I'm picking up from 100, right? So for me, what's 150 minus 100? That'd be 50, right? For you guys, I think it's just something a little different because I have that number boxed in. All right, I'll go ahead and write that on out. 150 minus 100 for me, and then probably something a little different for you. Degrees Celsius. Okay. Okay. All right, guys got that?
Wait,
okay.
Hold on 1 second.
Okay. That process working out? All right. Okay. I'm gonna switch ink color again. How about black ink? How about that? Okay. We'll say equals. Right. I'll get some number of joules of energy it takes for each part of this process, and I just add it all up. Okay. So let's do that grams times. Okay. Just gonna get some numbers here. That many joules. That many joules. All right. Okay. And finally, add this all up. Okay, now I'm getting so many, like thousands of joules, right? And I see all my answer choices are in kilojoules. So what do I have to divide by to get to kilojoules? Kilo is a factor of 1,000. Yeah. So can I just go ahead and call this that many kilojoules? Right. And that matches an answer choice on my paper. Bam. Right there. There. All right. Working out. Yeah. All right. All right. So two more. Let's do number 65. Got so many grams bullet. Lead bullet. Oh, and I told you guys the specific heat capacity of lead. Right? So how difficult is it to heat up or cool down lead? Okay? Moving at so many meters per second. So somebody fired this bullet, strikes a tree and is brought to a stop. Let's suppose that all the kinetic energy is converted to thermal, and furthermore, it stays in the bullet. So maybe kind of a boundary condition question. Right? What's the temperature rise of the bullet? Or maybe like, what's the maximum temperature rise of the bullet? It's probably a more realistic question. Right. But ooh, I think this one is a lot like the waterfall question. At the waterfall, there was some potential energy that was converted to thermal. Here, there's some kinetic energy converted to thermal. I'm still going to use this framework. Sum of energy initial equals sum of energy final, right? And I'm going to say kinetic energy, 1/2 mv squared, converts all to thermal. And okay, talking about a solid lead bullet, let's go ahead and call it MC delta T. Right? I mean, as long as it doesn't melt or something, right? We just stay along some like a T curve like that, right? Okay, right, you guys got that? Right. Again, that looks a lot like that waterfall question. That potential energy to thermal, now it's kinetic energy to thermal. Right. So, ooh, guys, does the mass of the bullet cancel out? It does. So if you had like a 3 times mass bullet, you know, if given it was the same speed, you'd still get the same temperature rise. Right? And temperature rise is the question. What is the change in temperature of the bullet? Okay. Okay. There's one more weird thing. I don't know why I typed it this way. Maybe I was intentionally trying to throw you guys a little bit of a curveball. Right? But you guys remember the base SI unit for mass is kilograms, and that's embedded in like joules, right? It's like kilogram, meter squared per second squared, something like that, right? But the specific heat capacity, yeah, I don't know why I did this. I listed it in joules per gram Kelvin, right? Which is a weird thing to do. So if you want to get the correct answer on your paper, you have to use joules per kilogram Kelvin. You have to multiply that number by 1,000, is what I'm saying. Here. And since I think we all have a lead bullet, so just go ahead and follow my notes here. Right. I think you have a different speed than I do, but other than that, right. So my bullet was going this many meters per second. Right. Now, specific heat for lead. Now, here's where, be careful about this. Use this number. Use 159, because that's joules per kilogram Kelvin. Right? Right. And then times delta T. Okay. All right. So let's see, square that times half, divide that over. Delta T is, see what I'm getting? So that times that squared divided by that. Right. Yeah, I'm looking at this many. Right. I could say either Kelvin or degrees Celsius. Either is okay because it's a change in temperature. Okay. See, do I see an answer choice that says something like that? Yes, I do. Right, here it is. Ba-bam. Ba-bam. All right. Are you guys getting an answer choice on your paper too? Yeah, yeah. All right, all right. All right, so let's do one more. And then, like I said, don't worry about the ones that we skipped. Although here, there's a backside of this paper. We're gonna save this for another day. So after we finish this today, just hold on to this paper and then we'll do the other ones another day. Right? The ones on the other side. Chapter 13. All right, here's our last chapter 12 question. Number 9. You guys see test number 9? Test number 9. You do so many joules of work, 0.05 joules of work on coffee in your cup every time you stir it. Okay, so we're like stirring sugar into the coffee, right? So just stir, stir, stir. Okay. Every time you stir it, you're doing some work measured in joules. Okay. What would be the increase in entropy? We're getting an entropy question. And so many milliliters of coffee at 65 degrees Celsius. Right, hold on to that idea. Right? When you stir it, like so many times, I have 30 times we're gonna stir it, stir, 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 stir. Okay. Okay. So you guys remember yesterday, I took quite a bit of time in the PowerPoint to talk about entropy and the second law of Thermo, right? There's a certain time order of process that you expect. Guys, can you stir sugar into coffee? Yeah, you do all the time, right? Can you unstir sugar out of coffee? No. Right? And what's the physics explanation? The second law of Thermo. Right? Oh, that's what we're talking about here with entropy. And I gave you guys here, it's test number 9. Right? I gave you guys a formula for entropy. It went like this: delta S. So it's a change in entropy is equal to like a energy transfer. Right? So I'll say energy transfer, which could be work, right? Work, right? Divided by the absolute temperature. Absolute temperature. Right. Now the catch is, has to be absolute temperature measured in Kelvin. Right. You can't plug in some number in Celsius, which is from a relative scale. That would give you a nonsensical answer. Okay. So the change in entropy, which we're solving for, is right. Well, I did 0.050 joules of work per stir, multiplied by, I'm stirring it 30 times, 30 stirs, some number of joules I transferred, right? Then divided by, now I have a 65 degrees Celsius coffee, but I can't just divide by 65. I have to add what to it? 273. Oh yeah, Aaron got it. Right. So that I can get some temperature in Kelvin. Now that gives me a temperature in Kelvin, right? That's the number. Let's try that. So that energy per stir times that many stirs divided by, and then open some parentheses here, the temperature in Celsius plus 273 to get it in Kelvin. Okay. I'm saying the entropy increase, right? Again, has just like disorder, maybe like what's the decrease in quality of energy? You can think of it that way, right? This many, and then this has a unit, joule per Kelvin. Joule per Kelvin. There you go. There's the increase in entropy by stirring, say, the sugar into the coffee. Right. Make sure I'm getting an answer choice on my paper. Oh, bam! It's right there. Oh, yeah. All right. Right. Oh, yeah, it worked out perfect. Right. We got a minute to the bell. Like I said, hold on to this paper, and then in the coming weeks, we'll eventually do the chapter 13 questions on the other side. All right, that's a wrap on today.